Okay, so good morning. We are back to 243. So let me just very briefly review what we've done the last time. We are in part 1, and we've reviewed some of the basic definitions up to the statement of the second law, and we have to pick it up from there. Just quick reminder, we said what we mean by the word system, and we explained that the word system is loaded with meaning. It's not just that anything can be a system, it has to qualify. In particular, there is a constraint on how the external forces should be mounted in your model. They must not depend on coordinates of external constituents of your system. Later on, we'll see that there is also another constraint relating to correlations. This means that your system should not depend on being correlated with some other system. If it is, you have to consider also the other system in order for it to be called a system in our little business, in our little theory. Then we define a property as being a physical observable, so something that you would obtain by probing your system in some way according to some recipe, some measurement procedure, and measurement procedures are what define these properties. And we gave the measurement procedure for energy, for example. We talked about what we mean by the word state. It's the list of numbers that give the values of the properties at one instant of time. And the time evolution is described by an equation of motion in a detailed model. But it can also be described by just an initial state, a final state, and a description of the effects that occurred outside of your system during that time interval. In either way, we have a few things to check. In particular, the important business of thermodynamics is that you have to check two things. One, the consistency with the first law, which would be a theorem in the framework in which you start from the equation of motion, theorem of the equation of motion. And you also have to check the second law, which would be another theorem of the dynamical equation. The idea of process, I already said, it's three things: initial state, final state, and effects on the environment of the system. And how do we account for effects in the environment? Well, the most we can say is how its state changes. Then, by defining a wave process, namely one in which the only external effect is the higher lifting or lowering of a weight in a gravity field, which is a prototype of a mechanical effect, we could introduce the statement of the first law. It is an ingredient of that statement. It says that you take any system and pick any two states of that system. They can always be interconnected by means of a wave process. Not always you can do it in the direction you want. But if you cannot do it in one direction, you can do it in the other. And that gives grounds for the definition of or support for the measurement procedure that we introduced to define the property energy. Without the first law, you couldn't assert that by making this procedure you get a property, value of a property. So essentially, this is the main, the most important consequence of the first law is the existence of property energy, which, yes, then it is additive, it can be exchanged between systems, and it's conserved. And that gives rise to the energy balance equation with this symbol, which you have applied in your undergraduate courses or previous. Every time we perform a model, we perform an energy balance to account for to check that the difference between the final and initial value of property energy is equal to the energy that the net energy that has been received by the system during that time interval. So that's a statement of conservation of energy. So some people call it, I write the first law, but I prefer to say I write the energy balance. Then we headed towards the second law by introducing this idea of classification of states based on how they change in time and why they change in time. Particularly, we focused on equilibrium for the moment, but later on we will focus on non-equilibrium. And there is equilibrium and equilibrium, and we define what we mean by stable equilibrium and metastable equilibrium. The stable equilibrium state is most important because it enters the statement of the second law, and it is defined as a state, an equilibrium state. So that means it doesn't move, it doesn't change in time, it doesn't move in state space, so it doesn't change with time. And you cannot change it without paying a cost, without having some net external effects. You need to spend something in order to change a stable equilibrium state. You cannot do it for free, so to speak. And here's the statement of the second law. It is also made up of two assertions. Let's start first with we'll focus first on the assertion one. It responds to the question, how many stable equilibrium states does a system have, in a way that is apparently contradicting what we know from mechanics, because it says that if you fix for your system the amounts of constituents, so that means the number of particles of each kind, and the values of the parameters, that is all the volume of the system or the other things that describe the external forces or the things that you can control from the external. So you fix this. Then for each value of the energy, there is one and only one stable equilibrium state. That is the statement introduced by, I think, by George Hatsopoulos when he was collaborating with Joe Keenan in the 60s in this department. We'll talk about this, the second assertion, in a moment. And we will see also, as we go on, that, in fact, there is no contradiction as long as we understand and we convince ourselves that thermodynamics considers a set of states that is broader than the set of states considered in mechanics. So within the set of mechanics, there's only one stable equilibrium state, which is the lowest energy state for the given values of n and beta. But in the more broader set considered by thermodynamics, there is one equilibrium state, stable equilibrium state, for every value of the energy. And this has consequences, important consequences that we will discuss today. Yeah, so one would ask, well, why? I mean, we already have statements of the second law. Why do you accept this other one? Well, that's because it is more general, and it implies as consequences, as theorems, the most famous statements of the second law, which are the Kelvin-Planck statement, called also a possibility of a perpetual motion machine of the second kind. This is the only thing we will prove today in some fashion, because it's easy. Is a direct consequence of the first assertion of the second law. Later on, not today, probably next time, we prove the other statement of the second law, which is Clausius' statement, the one that says that heat does not go from cold to hot spontaneously, but vice versa. That requires that we define what we mean by heat, what we mean by temperature. It takes a while, not long, but another lecture. But the beauty of this construction is that you get to that result as a theorem of combined first and second law. There is also another important statement by Kara-Theodori, which is more mathematical though, which can also be proved, but we will not do it in this course. Okay, so what is the perpetual... now I want to talk about Kelvin-Planck statement. What is a perpetual motion machine of the second kind? All right, it is any device, essentially a system in our language, that would start from a stable equilibrium state. Remember, a state that cannot be changed without leaving some net external effects. And end in another state, a different state, while in a weight process in which the weight goes up, so in which you have transferred some energy out of your system and into lifting the weight. Okay, if you manage to do that, it's a perpetual motion machine of the second kind. It's funny because it has been very long since I have not received any emails from these crazy inventors, but perhaps because I mentioned it, or maybe Google listens, or maybe that's because I'm at MIT. But on Wednesday, I received one. I'll be happy to show it to you. Very funny. Somebody who wants to put a container in the sea and it's not even a perpetual machine of the second kind. It's of the first kind, I would say. And I think the guy needs to learn some fluid mechanics, but in the old days, it was a continuous flow of applications for patents in violating this the impossibility of this thing. Until in the 60s or the 70s, I forget, the patent office, U.S. patent office, decided that anything that violates the second law or the principle of this principle of impossibility of Retienen 2 is rejected immediately without going to referee. That's because, as I may have told you, I forget the last time, but I remember when I was a student with Professor Hatsopoulos, he would be so well educated to reply in written and in full length to any letter that he would receive, which is a principle that I still have. But he would spend like 20 pages to explain line by line why you were wrong and what. And often these crazy inventors make very complicated and convoluted reasoning that makes it very hard to dismantle and reject. But he was doing that consistently. Whether it was asked by the patent office or by the inventor direct. Fortunately, we don't have that sort of spam any longer. So how do we prove this? Well, one simple way is to prove it if my system can be divided into two parts. So let's reason this so that we see also what kind of proofs, logical proofs are we're talking about. And it is a proof of absurdo, so that means we assume that the EMM2 is possible and show that it leads to a contradiction. So let's assume that our system, which can be divided in two parts, that also an additional assumption, can be removed, but it makes things more complicated. Assume that it does start from a stable equilibrium state, and it does end in a different state, A1, with as external effect the lifting of a wave. All right, if that's true, if that's happened, then you can take the energy of the wave back and use it to take one part of the system and accelerate it to some velocity. So give it in form of kinetic energy. Take the potential energy of the wave and give it as kinetic energy of the second part of the system. So what have we achieved? So look at this state and the initial state. Why is this not possible? Because the final state is different from the initial one, and the initial one was a stable equilibrium state. And there are no external effects, because the wave went up, but then it also went down. So the net external effect is zero, yet we managed to start from a stable equilibrium state and change it to a different state. That contradicts the definition of stable equilibrium. Okay. All right, so this is the proof of the Kelvin-Planck statement of the second law. Now, in order to go on the second aspect of this second law, second assertion, we left behind one of the definitions that are peculiar of thermodynamics, and it's that of reversible process. What do we mean by reversible process? Okay, the definition is as follows. You have a process, first of all, so it means you have an initial and a final state, and you have an external effect. B1 goes to B2. The state of the environment changes so much. Okay, the process is, we call it reversible if it is possible, not necessarily retracing it backwards exactly the same forward path of your initial process. But in any other way, if you find a way to bring the state of your system back to its initial, and also the state of the environment back to its initial state, then, and only then, we call the process reversible. Okay, so that means you have to try are all possibilities. So this is a very abstract definition, but it's also very precise. So I'm not going to do it because I want to make dust, but I usually take a piece of chalk and throw it to the wall, it breaks, and ask you, was that process reversible or not? What would you say? It's not. Fine. But how do you decide? I know it's intuitive.
I mean, I'm making an assumption that like the sound waves and all that other distributed better you can get them back together.
Good. Okay. So you use your physical intuition. That's because you have a background. You have already seen the idea of reversibility and irreversibility. But in our game, if you accept the rules of our game, what should you have done to decide? You should have tried to reconstruct the state of the piece of chalk to see if it is possible to place it back. And then also, whatever it did to the environment must be undone. And you have to try all possible ways. So how could you be so quick in answering? Okay, it's a correct answer, but you didn't apply our rules. This is to just underline that this is a very abstract concept and impossible in practice. It doesn't correspond to a procedure so that you can verify if a process is irreversible or not. But it's a concept. And soon we will find a method, and of course, as soon as we have defined entropy, that will be the method to compute, to calculate entropy, measure entropy, and see how it changes. And from the entropy balance equation, we can decide whether a process is irreversible or not. So we develop a practical method to measure this very abstract concept. So why is the concept of reversible process important in the second law? Because in the second statement, second assertion, it says, you start from any state of your system, and you can always go to a stable equilibrium state, so bring your system from that state to a stable equilibrium state, in a wave process, which is reversible. So it's all our concepts together. That's why we defined them before. Now we put them all together there. But if you go slowly and you mumble about it, that's what it says. We define all the terms. Start from an initial state. You can always get your system to a stable equilibrium state by the use of a wave process, a reversible wave process. Okay. Now, it turns out that if you try other ways to change your state to a stable equilibrium state, other ways that are not reversible, you would lift the weight less than when it is reversible. So that means this is a theorem. And it's proved in the usual book. And the theorem says that the maximum lift that you can give to a weight in a wave process with your system starting in any state is obtained when your system ends in a stable equilibrium state and when the process is reversible. And that final stable equilibrium state is uniquely fixed by your initial state. There's only one stable equilibrium state that can be reached in a reversible wave process from state A1. So this is enough to say that the amount of energy that you transferred to the wave in these conditions is a property. It depends only on state A1. So it depends only on time T1. Because the final state is a function of A1. So it also depends on T1, on the state at T1. And we call this property adiabatic availability of the system in state A1. It's the maximal, I don't want to call it, but we could also call it work, because eventually that's a work interaction. So it's the maximum work you can extract from your system in the given state. And if you are an engineer and you're trying to make devices to exploit natural resources like energy resources like coal, natural gas, nuclear, whatever, solar, the main question that thermodynamics was set for 200 years ago by Carnot is, well, what's the most I can do out of this situation? And adiabatic availability is an answer. Of course, it gives an answer under certain conditions. You change the conditions, you get different answers. As we will see, we will have more availabilities. It depends on the condition. Here, the condition is in a wave process. So if I have my system and I confine myself to just a wave process, that's the maximum amount of energy I can extract from my system. The most I can do out of it. If it weren't for an important detail, we would be satisfied that adiabatic availability is all that we need in order to describe our engineering applications. The detail is that this property is not additive, and therefore it's not very practical, because when you have a system made out of two subsystems, and you measure the adiabatic availability of system A and then the adiabatic availability of system B, well, if you want to consider the combined system, you have to make another measurement to measure the adiabatic availability of system C. The simplest example that I can think of is, suppose you have a glass of water which is hot and a glass of water which is cold. So you measure the adiabatic availability of this one, and if it is hot but in a stable equilibrium state, how much is the adiabatic availability? It's 0, because otherwise it would be a PMN2. No? I mean, if you started from a stable equilibrium state, you cannot lift the weight. So a system in a stable equilibrium state has 0 adiabatic availability. So the adiabatic availability of, we use the letter psi, so of this glass of water is 0. Also of that glass of water is 0. But if I consider the composite system, of course, we all know that, for example, with the Carnot engine, you can extract work out of this situation. So you see that 0 plus 0 does not make a number different from 0. So we lack additivity of this property. And this is why it takes the next half hour to build up another property. It will be entropy, which will contain features so that we can compute the adiabatic availability, and it will be additive. So we have to build additivity on around adiabatic availability. There is also this other theorem that I'm not proving, but I'm pointing you at this proof. It's on page 76 of the book. Again, so since I'm not doing it, I'm not asking that you study it, but if you're curious, just go and look. And it says that if you consider a weight process, so now we confine ourselves to a weight process, between any two states, okay? So, clearly, since our adiabatic availability is a property, you can measure it for state A1. You could also measure it for state A2. Like energy, the property, so you can measure it for A1 and you can measure it for A2. So you give me two states of system A, and I can measure for each state its energy and its adiabatic availability. So it turns out that this theorem says that if you have a necessary and sufficient condition for the process to be reversible, if the difference between energy and adiabatic availability, so you could interpret that as the energy that is not adiabatically available at the end is equal to the energy not adiabatically available at the beginning. So, in a reversible process, the energy not adiabatically available is conserved. Whereas in an irreversible process, it increases. Very similar, in fact, also entropy will play the same, will play in a similar way. So this energy not adiabatically available is a weakness of reversibility. It's the basis for measuring in practice whether a process is irreversible or not. All you need to do, is, according to, if you trust this theorem, is measure energy, measure adiabatic availability with the tools we developed, and then check this inequality. If it is an equality, the process is reversible. The weight process is reversible. If it is an inequality, like this one, the process is irreversible. If it's the other way around, it's impossible. It made something wrong. So it is impossible to decrease the amount of energy that is not adiabatically available. Okay? So this is a precursor of the principle that we will call of entropy non-decrease. We could call it the principle of non-decrease of the energy adiabatically non-available. Okay, so now we try to make or build up this property that has that builds additivity into adiabatic availability. So we are heading towards an 8. In order to do that, we introduce some other concepts. The first one is the concept of mutual stable equilibrium, or mutual equilibrium between two systems. So two systems are in mutual equilibrium, like the hot and cold. These are not in mutual equilibrium because the composite system is not in a stable equilibrium state. The fact that it has adiabatic availability, because that's an if and only if theorem, so the fact that it has non-zero adiabatic availability is equivalent to not being a stable equilibrium state. So these two, they are individually in stable equilibrium, but the composite is not in a stable equilibrium state. So they are not in mutual stable equilibrium. In another situation in which instead they are individually, and also the composite system has zero adiabatic availability, so that means the composite is in stable equilibrium, then you say that the two systems are in mutual equilibrium. That's the concept. The other concept is that of thermal reservoir. A thermal reservoir is a particular system, I would say a limiting system, that has this feature that I will describe with a practical system that you make in any lab. You take the substance, like water, in a fixed volume container, and you produce a combination that we call triple point. So a situation in which you have the coexistence in stable equilibrium of ice, liquid water, and water vapor. Like here, ice, liquid water, and water vapor. Okay. Then you find another system, let's call it C, that is in mutual equilibrium with it. For example, it could be another copy of another piece of water at the triple point, but not necessarily. The important thing that defines a reservoir, a thermal reservoir, is that if you change the energy of this particular system, for example, I consider a state with more energy, so it will have lesser ice, maybe a little more water vapor or less liquid water. In any case, so the proportions of the three phases change. So these are two different states with different energies, but they are both in mutual equilibrium with this system C. Why did I choose triple point water? That's because it is easy to prepare in any lab. And as you know, we haven't defined what the temperature is. In a moment we'll do it. But just because you know what temperature is, triple point is at a low pressure, like 0.6 kilopascal, and at a temperature of 273.16. So it's 0.01 Celsius. Okay. So now that we have the reservoir, we apply again the second assertion of the second law, which says we can only start from a system in any state and reach a stable equilibrium state in a reversible wave process. This is an important loaded statement. It allows it. I mean, how do I know that it always exists? Okay, it's very abstract, but it's very similar to the statement that says in the first law, the second assertion, that says yeah, you can always interconnect the two-wave process, the two states by minimal wave process. But no matter what wave process you choose, it's always the same energy that you transfer out to the wave. How do you know that? Because I can invent many different ways to do their job, and how do I know that they will all get the same outcome? Okay, that also is a very abstract idea, but it works because energy, after all, has been very successful in describing stuff in physics, and we believe it so much to be one of those great conservation principles that we talked about last time. And here is the same thing. We have a very abstract idea about the existence of something. It guarantees that now we define a measurement procedure based on this one. If we didn't have this statement, we couldn't trust our measurement procedure. And the measurement procedure is based on this ingredient, which I repeat here with a little more detail. So I take a system and the reservoir. And they are in some initial states, A1 and R1. The reservoir starts in a stable equilibrium state, like water at the triple point. Then I do a reversible wave process for this combination, for this combined system, composite system, which has only external effect, the lifting of the weight. And it's maximal with lifting because the process is reversed, because it's the weight process is reversed. So that's the maximum. We are applying essentially the theorem of adiabatic availability here. But to the composite system, A and R. All right, if this lifting is maximal, I think I jumped a little bit, but maybe I could say that if the final state, in order to apply the theorem of adiabatic availability, the final state would have to be a stable equilibrium state for the composite system now. And by our definition of mutual equilibrium, it would mean that since the composite is in stable equilibrium, the two parts are in mutual equilibrium. So it means that in the final state A2, the system A is in equilibrium, mutual equilibrium with the reservoir. Here, I want to do it a little more general, and you see, I'm applying that theorem twice because I'm going, in order to go from A1 to A2, I could, in which my reservoir is in R1 and here is in R2. So now I do consider the composite of the two systems. The theorem of adiabatic availability says that if I go, let's say let's call it R. Okay, so if I go from here to here, and this one is a stable equilibrium state for the composite, then I have extracted as much as I could. Also, I can do it starting from state 2. So here I would extract the adiabatic availability, let's call it C11 of the composite system AR. And here I would have extracted the adiabatic availability of the system in this other state, 2. Okay. But since in doing this extraction I'm using reversible wave processes, I can also reverse the arrow. So I can go this way. And of course, I undo the effect on the weight. So as I go from here, so that means I can go from here to there by means of that reversible weight process. And the amount of energy I transfer to the weight is psi 1 minus psi 2. Okay. However, in this, the ingredient, yes, so we know how much energy we transfer to the weight in that process on the slide. But for the measurement procedures that we are going to introduce in a moment, what's important is the change in energy of the reservoir. How much did the energy of the reservoir change during this process? Because that's something that we can measure. So you do that process. So you give me a system A, choosing two states, A1 and A2. The second law guarantees that you can do this process with any reservoir. And then once you've done it, you can measure energy because we define property energy. And so measure it for the reservoir and make the difference of the final energy of the reservoir and its initial energy. Now, this symbol here is complicated because because I want to emphasize that, yes, we are measuring an energy difference for the reservoir, but it's more than that. We have to do it in those particular conditions. So it says that system A starts like this and so on, that the process is a weight process and that it is reversible. You do it under other conditions, it's another story. Okay? All right. So this is the ingredient. Okay, with that ingredient, here is the measurement procedure that defines a property that we will call temperature of the reservoir. And that will turn out to be a constant for a given reservoir. So equal for all of its stable equilibrium states. We already know that for the triple point water, it's 273.16 K or 0.01 Celsius. And in fact, it is for as long as you, in the box, you have all three phases, you can put in energy, take the energy out, and so on. As long as you have at least some ice, some water, and some water vapor, that temperature doesn't change. So it's equal for all the states of that system. Okay, but how do we measure it? Okay, so now for this measurement procedure, the object of measurement is the reservoir. You come to my lab with your reservoir and I am supposed to measure this property for your reservoir. So here's the object. In order to do the measurement, I take an auxiliary system. So I choose whatever system I want and any arbitrary two states for that system. And I do my reversible weight process for the combination that will list the weight by some amount. And I measure how much your reservoirs changes in energy. And I put that in the numerator. In the denominator, I put the result of a similar measurement that I have done once and for all for a reference reservoir, which I happen to like to choose the triple point water. Of course, when I did this measurement, I used the same system A and the same two states A1 and A2. Okay? And I measured how much energy changes this reservoir, reference reservoir. And I take this ratio. So this ratio is a measurement by comparison. It's exactly like when you say, well, how long is this thing? Okay, you compare it with the meter or the inch. Okay, and the meter is another object that is maybe in some museum in Paris, and you see how many times this thing stays. So take the ratio of this length to the length of the meter. You get a dimensionless number. It's exactly like here. It's a dimensionless number. And as you know, when you have measurements like that, you can introduce a unit of measure. You call the meter 1 meter, but you could have called it, I don't know how many inches are in a meter, but you could call it like 40 something inches. Okay. In this case, we take the ratio, we multiply, we take as a unit not 1 Gibbs or 1 Hatsopoulos, what we call it, since Kelvin was the first, we call it, and he didn't put 1, but he put 273.16, all right? So that's our basis. So we put here this number, and the result, so you multiply by that number, this dimensionless ratio, and you get this property, temperature in Kelvin. Of course, there is an important theorem, again proved there, that says, first of all, that this ratio is positive, that it is independent of the initial states of the reservoirs, that it is independent of your choice of auxiliary system, and once you've chosen that system, independent of the initial and final states A1 and A2 of that system, and also that it is equal for all states, stable equilibrium states of the reservoir. So that is a property having a constant value. We call it the temperature of the reservoir. Notice we define just the temperature of the reservoir. We haven't defined yet the temperature of a stable equilibrium state of a general system. Not yet. But this is enough for our purposes. Also notice that by the way we define the property, because this formula, you can rewrite that formula by taking the things with the subscript R on the left hand side and subscript R0 on the right hand side. You get this other equality. From this equality, you can infer that if I measure this ratio for reservoir R, it's the same as for the reference reservoir. It's the same for all reservoirs. So it's independent of the reservoir. So this ratio, although we use the reservoir to measure it, is independent of the reservoir. So what does it depend on? It depends only on the system A, the auxiliary system that you have used, and the two states. This is why this is very important, because essentially this leads us to the definition of entropy. That ratio, we call it the entropy difference between two states, A1 and A2, of our system A. If you want to put it in another way, what's the measurement procedure for entropy? Okay, so now you come to my lab and bring your system and bring the system in a given state on which you're interested in measuring the entropy. Again, I tell you, look, I just can measure entropy differences, so it will pick a reference state A0, give it whatever value you want for the entropy of that one. I'll measure only the difference. And how do I measure the difference? Well, I find a reversible wave process for your system and my reservoir. For example, I could choose water at a triple point, but not necessarily. And measure the energy change of the reservoir using this process and put it at the numerator. In the denominator, I put the temperature of the reservoir that I have previously measured with that other measurement procedure. And this ratio we just proved is independent of the reservoir I had chosen here. So I add this ratio to... So this ratio essentially is the answer. That's the difference in entropy between these two states. All right, so we have an explicit measurement procedure that gives us entropy. And the advantage of this property with respect to adiabatic availability is that it is additive. You do it for a system A, you do it for a system B, and then you do it for a system composite AB, where the entropy is the sum. The entropy differences are additive. In a moment, we will see also a practical engineering meaning of entropy. But let me also define this other property, which we essentially already did here. When you have a system in combination with a reservoir, like here, system and a reservoir, they start in some initial states. The reservoir in a stable equilibrium state, system A in any state, the equilibrium, non-equilibrium, doesn't matter. I can apply the theorem of adiabatic availability to the composite system and find that the maximum weight lift that I can obtain from this composite system in those initial states is the adiabatic availability, is obtained when we make the reversible the wave process reverse. And it also ends in a stable equilibrium for the composite system. So when the two, when A and R are in mutual equilibrium. So here, system A ends in a state that I call A sub R, just to remind us that it is the state in which system A is in mutual equilibrium with the reservoir. And the final state of the reservoir is also uniquely fixed by the initial states of A and R. Okay, this is a new property. You can view it. If you fix the reservoir, or with respect to a given reservoir, this is another property for system A. It is another availability, it's another maximum work in other conditions when the system can also interact or has a reservoir available with which to interact. We call it available energy with respect to the reservoir R. we can make, we call omega. Omega is the energy that goes through the weight. You can write an energy balance for that process, because now we know how to compute the energy, so we can compute the energy difference for system A. It goes from A1 to AR. So the energy that goes out of system A is E1 minus ER. The energy that goes out of the reservoir is the energy of R at state S1 minus the energy of R in this final state. And since energy is conserved, if these are the things that go out, they sum up to what is received by the weight. So this is the energy balance. But now if you remember how we defined the entropy of system A, just previous slide, it's the ratio of the energy change of the reservoir. So it's this much. The change is actually final minus initial, so it's minus this much, divided by the temperature. So that's the entropy. So this ratio, which you could substitute this part using this equation and make an expression for the available energy in terms of the entropy. I hope to see the algebra here. So this is the working equation for computing available energy of a given system. All you need to know available energy with respect to the reservoir R. You need to know the initial energy, the initial entropy, E1 and S1. You need to know the energy and the entropy that the system has once it gets into mutual equilibrium with the reservoir, and you need to know the temperature of that reservoir. And this is the combination. If you, we call it available energy with respect to the thermal reservoir. Later on, when we say a few words about exergy, and this is one form of exergy. Exergy is a word that was invented in the 70s or maybe earlier. Keenan called it availability in 1941. So this concept is been around for a while. But exergy, the X means it's like the essential part of energy, because essentially exergy is the answer to the question, what's the maximum I can do from a given situation? So there are many exergies, and we already have seen a couple. Adiabatic availability is an exergy that applies when the system undergoes just a wave process. Here we have available energy. It's another exergy that applies when the system also is available a reservoir. It is the combination of the system and the reservoir which undergo a wave process. So this is the formula. So let's play again here. Let's play a bit with that formula and rewrite it in this way, putting in evidence the entropy of state 1 of the system. Yeah, before I do that, notice that except for the temperature of the reservoir, this formula doesn't have any other properties of the reservoir. Doesn't have the difference in energy has disappeared, because we wrote that in terms of the entropy change for the system. Okay, so we put in evidence the entropy of system A, state A1, and we notice that except for some things that are constant, fixed by the chosen reservoir, the entropy is proportional to the difference between energy and available energy. So again, it is the energy that is not available with respect to the reservoir divided by the temperature of the reservoir. So the entropy is proportional to the non-available energy with respect to a reservoir. So the higher the entropy, the lesser the energy that can be transformed into lifting a weight, which is the prototype of a useful effect, mechanical effect. Okay? So that's why I call it engineering of entropy. A lot of mechanical engineering, energy engineering is related to trying to exploit as much as possible the availability of systems, in other words, to an entropy plays against you. If you let entropy increase, you lose ability to do useful effects. So that's why in engineering we have to work in trying to improve the efficiency of stuff, of machinery and so on, with the purpose of reducing the spontaneous generation of entropy, because that will kill the available energy. Okay, we already said that entropy is additive, that it can be proved that it is additive. And the theorem on the criteria for reversibility. We already see the first line here, expressed in terms of adiabatic availability of the system. You can express the same, that theorem translates also for available energy. So the difference between energy and available energy with respect to any reservoir, any given reservoir, remains constant in a reversible process. So the unavailable energy remains constant in a reversible process, while it increases in an irreversible process. And it cannot decrease. And since we just saw that this unavailable energy is proportional to the entropy, we can write this as S remains constant in a reversible weight process. Entropy increases if the process is irreversible. Entropy cannot decrease in a weight process. Be careful here about the conditions that we make this statement in, because it would be wrong to say, the entropy cannot decrease. The entropy decreases all the time. Whenever you take a can of Coke and put it in your refrigerator, the entropy of that can of Coke decreases because you are cooling it down. That is not a weight process. What we're saying here that the entropy cannot decrease in a weight process if the only external effect is only the changing, the lifting or lowering of a weight, then you cannot decrease the entropy. But you can decrease the entropy of your system by simply making it flow out of your system, because entropy is actually transferable. We prove that in the same way as we did for the transferability or exchangeability of energy. You consider a composite system, you apply if I do it for a reversible process, then entropy remains constant. So it's a principle entropy conservation in a reversible wave process. You combine it with additivity, you find that the entropy cannot disappear. If it goes out of system A, it means that you find it somewhere else in system B, in a reversible wave process. So, in the same way as we decided to give a symbol to this amount of entropy that is transferred from one system to the other, we use a symbol that is similar. So S for entropy transferred from B to A in the direction of the arrow. So it's a positive number if the flow is in the direction of the arrow. Otherwise, it's a negative. And so we can write this as a balance equation. A balance equation. For a reversible process, you wouldn't have this part. You would simply say that if there is a change in entropy of your system, it is due to the amount that it has of entropy that has been transferred with its environment. But then entropy is not really always conserved. It's conserved only in a reversible process. In an irreversible process, it's not conserved. And if the process is a wave process, it can only increase. So that means that the entropy change of my system can be greater than the amount it received, but cannot be lower. So essentially, we are writing an imbalance equation. A balance equation, if you want, it becomes a balance equation if you put in the balance also the imbalance by calling it entropy generated or produced by irreversibility. And this brings us to the entropy balance equation. I assume that you have played with this in solving problems in undergraduate thermodynamics and in your applications in energy or exergy analysis, any technological problem having to do with energy transformation of energy various forms requires you to make not only an energy balance but also an entropy balance. And the combination of the two is what allows you to determine things like how good am I doing, what's the efficiency of what I'm doing. So these balance equations, as we see more explicitly, are the fundamentals to define efficiencies of power plants and any device that does transformation of energy. Okay, this is also the version of the entropy balance, a right version of the entropy balance. If you have the kind of description in which you can follow as a function of time the state of the system, therefore you can measure as a function of time the entropy, and also how much entropy is being exchanged. So the rate of entropy exchange. And remember that in an entropy balance, there are three very distinct elements. There are three parts of that equation. The left-hand side says how much the property changes from the final to the initial state. The transfer term says how much the system, the net entropy that has been received by your system or exchanged, if it is negative, it's given out by the system, due to interactions. It's a flow of entropy going in and out of your system. The last term, instead, is the generation. It occurs internally to your system. It's the dissipation. It's the waste that occurs if you let things move around. For example, if you take Irish coffee, it's very nice until it is separate. First time you see it, you were excited. If you stir it, you lose the beauty, no? And by stirring it, you have mixed up things. You have produced generated entropy. You lost, the beauty, because you are sort of drunk, and so that's. But this gives the idea of the fact that stirring is something that happens spontaneously. If you help it by stirring it goes faster, and it's something that you cannot undo. The Irish thing will not separate, maybe three, but not if you're talking about energy applications. So if you're not careful enough and things get stirred up, you lose opportunities to convert the energy and to extract energy out of your source, and you've lost it forever. Okay. Luckily, I don't think today, but the next time we will be able to introduce a graphical representation of all that we have said that is very useful to remember and to reason the various consequences and also to set up problem solving and answering additional questions. It will be the energy versus entropy diagram. But we are still building up material so that we can use that diagram to summarize what we have seen so far. And one of these ingredients that we still need is another theorem that is called the maximum entropy principle, which says that among all the states of a given system, once you fix the values of the amounts of constituents and the parameters of the external forces, and you consider, of course, you remember that if I fix the amounts of constituents, let's call them n of t. Let's forget the t, n, and beta. This doesn't fix the state, because the state is these numbers plus the values of all the conceivable properties. Most of the times, this list is an infinite number of numbers. Okay, so fixing just these two leaves you again with an infinity of states. Now, suppose I fix also the value of the energy. Okay, so I fix this much. Still, I have a lot of states. They will differ in the values of all these other properties, but they have the same energy. Okay, so if I consider all these states that have the same energy, amounts of constituents, and parameters of the external forces, it's a set. In this set, the second law, first assertion, says there is a unique stable equilibrium state. This theorem says that state has also the highest value for the entropy. And it's a strict inequality. It's the only state that has that value. All other states with the same energy and so on have lesser entropy. The stable equilibrium state among these ones is the one that achieves the maximum value, and it is the only one that achieves that value. This is called the maximum entropy principle. There is also a dual principle that is called the minimum energy principle. It's similar to this one, except that here you put S. So if I consider all the states of a system that have the same given same values of n, beta, and the same entropy, then among all these states, there is one stable equilibrium state only, and it is the lowest energy. When you fix the value of S to 0, that corresponds to the domain of mechanics. And that minimum energy stable equilibrium state is the only one. And so then we recover the minimum energy principle of mechanics. But thermodynamics is about states that have also entropies different from 0. And so we have a more general minimum entropy principle. Yes?
In that, therefore, we're basically saying that when we reverse roll processes, the state that means that it will do is home.
Yes. If you start from the low, a stable equilibrium state, like this one is a stable equilibrium state. If you spend some work, so if I go this direction and I spend some work, I can obtain any other state, but only those that have the same entropy as I started with. If the process is reversible, the entropy will remain constant. So I can go from my minimum energy stable equilibrium state to any other state which has higher energy because I put in some work. But if it is reversible, it has the same entropy. If it is irreversible, it will have higher entropy. So I can go only, let's say, if I'm here with energy, I can go up, and this is entropy, so this will, okay. So I start with a certain value of the entropy, say S R. I can go up in a reversible process to values of the energy higher than I started with. So this is ER. Or I can also go to the right because I put in energy, but if the process is irreversible, I generate some entropy. So the entropy adds, and I go to the right. So yes, thanks, because this anticipates essentially this energy versus entropy diagram, and which is useful because, as you know, a picture is worth 1,000 words, and this is the picture that allows you to answer this kind of questions. The last ingredient that we need in order to go to that graphical representation is called the state principle. again, it is a consequence very directly from of the first assertion of the second law, which says you fix n and beta, no? Fix n and beta, you fix the energy, and once these are fixed, there exists a unique stable equilibrium state.
Okay.
All right, the last S means state. So, yes, it's a state which is stable equilibrium. So what does it mean, state? State means the values of all the properties. So that means that this thing fixes the values of all the properties. Of course, we're talking about of a stable equilibrium state. So mathematically, that's exactly what we mean by a function. The properties, it means that these properties, any property, is a function of these numbers. If these numbers fix the value, that's what we mean by value of a function. So we can write any property of stable equilibrium, at stable equilibrium, as a function of the amounts, the parameters, and the energy. And since among the various properties we defined entropy, we can also write that for the entropy. So we can say that for the stable equilibrium states, the entropy, the value of the entropy is fixed, like all other properties, by the amounts of constituents, the parameters of the forces, and the energy. This expression, this formula, this function, is called the fundamental relation for the stable equilibrium states. In some old-fashioned books of thermodynamics, this function is page 1. You take the book by Cullen. Cullen was a PhD from MIT also. Very nice contributions. But in his times, thermodynamics was only about stable equilibrium states. And so that's the starting point. And since I'm at it, why not say and reminding you that instead we've seen a definition of entropy today, in which you may or may have not noticed, but I will stress it anyway, that we never said anything about how many particles the system should have. In our game so far, we could have a system with 1 particle or 10 to the 23. It could be just water in a box or a nuclear power plant. Complex or simple. Small or large. Plus, we didn't make any assumption about the kind of state. In fact, the most interesting states are those that are not stable equilibrium, at least from the point of view of making a wave process. Because in a stable equilibrium state, we just have seen that the perpetual motion machine of the second kind is impossible. You cannot extract work. So not very useful from an engineering point of view. And that's why consider the ocean as a thermal reservoir, not the waves. That's a different story. But as a thermal reservoir, and if you forget also the fact that inside there are temperature gradients and also salinity gradients and so on. But if you think of it as a huge system, so it has a huge amount of energy, but that energy is essentially useless. The thermal energy is useless because it's in a stable equilibrium state. Whereas if I have a system in a non-equilibrium state, and I'm quick enough to extract its adiabatic availability, I can do something useful. For example, we will do later on, in the second part, we will do like chemical reaction. When you think of what happens inside your internal combustion engine. You got the piston, you got a mixture of air and gasoline, and you light the spark. At that moment, you produced a non-equilibrium state, which very quickly, in a matter of milliseconds, will interest the entire combustion chamber. Pressure will go up and so on. The internal combustion engine is an incredible device that has been there for a century now, maybe longer, and it's still powering our cars. And because it's a smart way to extract the availability. It doesn't do the entire job, though, because it loses the opportunity that you have from when you light the spark to when the flame is engulfed the entire combustion chamber. That is a very reversible process, and that's where you lose the about 60% of your availability, no? Because internal combustion engine is 40% efficient, so that means that I lost 60% somewhere, and that's where I lost it. So, non-equilibrium states, and so we define entropy also for non-equilibrium states, which is most important for the more modern applications of thermodynamics, and that's why we're here. Actually, I was very happy just yesterday to receive an email. I think it was sent to the entire community, not very special, but an email from the MIT president announcing this initiative about climate. Okay. A lot of the applications that will come out of that project in the future will have to do with energy and the best use of energy. Okay, not only CO2 segregation or greenhouse gases, but all the crazy ideas that people are talking about in trying to control, for example, the amount of heating that comes to the sun. There was an article the other day in the New York Times talking about people that want to build shields in space, to reflect away some of the power of some of the photons that come from the sun, so that you could control temperature. Of course, you will need a surface to. I think it was the surface of the entire Argentina, which is essentially half of South America, somewhere put in a place which they call it Lagrange place or Lagrange spot, where it would stay because the gravitational force from the sun and from the earth is the same. All right. So, yes, crazy ideas. But one tool with which you have to evaluate these ideas and see if they are feasible or not is precisely what we are doing here. For any energy technology or for any technology, you have to see that you're transforming forms of energy, you're spending energy to recover another effect. You have to define efficiency, feasibility, and efficiency are very important, no? Because if the amount of energy you're consuming for a certain task is more than the work, minimum work to do that task, it's worthless. You better not do it. Do it in another way. Okay. So what I'm saying is that somehow by learning these tools and ways to understand equilibrium and non-equilibrium for large and small systems, you are in good position to go and contribute to this very bold MIT project, MIT enterprise for the next 10 years. So that brings me to one more thing, and then just we have 3 minutes. Once I have a function like this function here, then I can apply all the tools of mathematics. For example, if I'm interested in looking at how the function behaves in the neighborhood of a given point, so here's the function, and I'm here, and I want to see how it behaves in the neighborhood by changing one of the variables, for example, the energy. Right? I can write a series expansion on the function. I take derivatives, first, second order. If the function is regular enough so that it's going to take at least the first two derivatives to respect all the variables, you're in good shape. And in practice, in most of the models, the function is analytic, so it has all derivatives. Some of these partial derivatives will turn out to be useful and to be important in determining necessary conditions for mutual equilibrium between systems. And it turns out that all the first derivatives, the first partial derivatives of this function here, play a role in determining those mutual equilibrium conditions. And that's why we give names. For example, the derivative of S with respect to E is the inverse of what we will call the temperature of the stable equilibrium state of the system. Yeah, that's because I write it also this way, as a derivative of S of E with respect to S, because once you have a function, and if it is well behaved enough so that all the derivatives are not either zero or infinite, you can invert the function. Okay, there are mathematical theorems for inverting function. So if I have this function of S as a function of E, I can also most of the times write it as E as a function of S. If I can do that, not for all systems, we'll see you can do that. But if you can do that, then you have another version of the fundamental relation, which is the energy form, because it makes energy explicit and entropy becomes an independent variable. And you can also take derivatives of this one. So the partial derivative of E with respect to S is going to be what we call the temperature of the stable equilibrium state. The partial of E with respect to N is going to be the total potential or chemical potential, depending on situations. And if one of the parameters is the volume, the partial of the energy in respect to the volume is what we will call the pressure with the negative in front, sign in front. So these partial derivatives are related to conditions for mutual equilibrium and are also therefore related to instruments with which you measure them by exploiting the mutual equilibrium condition. So you have the thermometer, the manometer, and the a manometer that allows you to measure partial pressures so that you can compute mechanical potentials. All right, so we are out of time, and we stop here. So next time we go to the energy versus entropy diagrams to summarize all that we have seen and go further.